Oh, you can focus better than that. There you go. So we've discussed creating some power series, knowing what you and I know about geometric series. Let me give you a second technique. Now, just so that you're aware of this, particularly in a testing environment, I'm going to refer to the technique I'm going to show you next as the brute force technique. For generating a power series representation for a function. So this new technique starts as such. Let's you and I assume that we have a function that's analytic about x equals a. Fancy way of saying, let's assume f does have a power series representation. Then it's going to look something like this. Now, I use that word something because, technically speaking, I don't yet have a handle on what these coefficients that I label c sub n look like. So my job right now is to show you, the reader, what these c sub n's do look like relative to the function f that was given. So would you agree in expanded form, if I substitute 0 for n, does that give me this? The sum means add to that what I get when the index variable raises by 1 unit, that is to say, when n is equal to 1. Plus the same darn term when n is equal to 2. It's an infinite series. I sometimes subclassify this as a Taylor series. If a happens to be the very special number 1, I sometimes refer to it as a Maclaurin series. Now, if I don't look at the infinite collection of terms, but say, for example, just look at the first finite number of terms, I might refer to that as a Taylor polynomial approximation or a Taylor polynomial representation for f up to the 3rd degree. I might even say up to 4 terms. And of course, I'd have a Maclaurin polynomial at degree 3 if I have everything you see here above the brace where a is equal to 0. So like I said, I'm the one who needs to come in and get a handle on what those coefficients look like. Allow me to get started. I have expressed my function f in expanded form. I've computed the first, second, and third derivatives. Again, something really nice about power series is that differentiating and anti-differentiating term by term are just a piece of cake. Now check out what happens next if I take my function f and divide it to a. If I do, every single term on the right-hand side completely drops out, except for the first one. With my first derivative function, my second derivative function, my third derivative function, there too, as I value them at x equals a as well, notice how here too, on the right-hand side of each of those 3 equations, every single term completely drops out, except for that first constant term. Here, here, here. So generalizing from this, can't you see or look ahead, playing a little bit of chess, that the nth order derivative, ev at x equals a, is simply going to be of this form, which is nothing more than n factorial times c sub n. Now take a peek at that relationship. Rewriting, what I'm really suggesting is this. If f is indeed analytic about x equals a, the output of f can be expressed in this form, where, more specifically, c sub n can be expressed as a ratio of the nth order derivative for f, ev at x equals a, divided by n factorial. This is going to be how I generate a Taylor polynomial representation for my function f, or a power series representation for f, centered about x equals a. I'll just classify it as a Maclaurin series if a happens to be 0. How about if I now provide you with an example?